Hey guys, it's Bruno, the IB math teacher. So we've just crossed the 50% mark. We went through the first 5 weeks. Now we're going to start week number 6 of the Ace Your IB math exams in 10 weeks. First of all, congrats. It's challenging, it is hard, the questions are hard, but they do prepare you in a very good way, in a very realistic way for the upcoming IB math exams with all sorts of questions, all styles of questions, with all topics, paper 1, paper 2, number and algebra, functions, you name it, everything is there. And we're going to continue that. We're going to continue for the next 5 weeks. So this is week number 6. If you've missed any of those, you can find the links for these videos and the PDFs in the description of this video right here. Everything is for free, and do share away. Share it with your colleagues, with your friends, so you guys can study together. And yeah, without further ado, let's get to it. Week number 6 of the Ace Your IB Math Exams in 10 Weeks challenge. All right, so let's jump to exercise number 1. In exercise number 1, we have a few log properties to use. So this is going to test exactly how comfortable you are with logs. So we need to show that log of root of 8 base 2, which by the way you can find quite fast, plus log of root AB base B is equal to this. Now, as I mentioned before, you can break this exercise into 2 parts and solve this first. We know what log root of 8 base 2 is. It is the number that we raise 2 to in order to get root of 8. Now we can write root 8 as some power of 2. In this case, given that 8 is 2 cubed, and given that square root is the same as raising to the half, or to the power of 1 over 2, what you're asking yourself is, 2 to the power of what is 2 cubed to the power of half? Now do remember that when you have a power over a power, we multiply the exponents, which means that this is the same as 2 to the 3 over 2. Therefore, your x value is just that. It is 3 over 2, which means that this blue box is 3 over 2. Now, going back to the question, we have 3 over 2 plus the log of root AB base B. And by the way, let me write the exponent property that we used over here. So b to the a to the c is the same as b to the a times c. And from here to here, the property is if log a base b is equal to c, then a is b to the c. Now going back to the exercise, do notice that on the right hand side we have lns, which means natural logs, or log base e. So it looks like we have a long way to get there. One of the things that we can do over here in order to see this process of going from the left hand side to the right hand side is to use firstly the following property. When we have log a to the c base b, we can drop the c. So this is the exponent property of a log. So we have over here the root of AB, which by the way, it is the same as AB to the half. So this is equal to 1 over 2 log of AB base B. So we have 3 over 2 plus 1 over 2 log AB base B. Now we have another property here, and let me not use A, B, and C for this particular exercise, or especially A and B, because they're already being used here. So let's just call them x and y and z. So let's say that you have log of xy base z. You can rewrite this as log x base z plus log y base z. You can go back and forth, so from left to right or right to left, of course, which means that over here we have log a base b plus log b base b, which by the way is equal to 1. So we have 3 over 2 plus half log a base b plus half. Don't forget to FOIL this 1 over 2. So we have 2 plus half log a base b. We can apply the change of base formula over here. Let's say we want to change the base from z to y, for example. This is equal to log of x base y over log of z base y, which means if we want to change this base to base e, which is exactly what we want actually, to use a log with base e, which is to have natural logs, we get 2 plus half log base e of a over log base e of b. You can write log base e or just ln, they're both fine. Now we write a common denominator, which is 2 ln of b. So we get 4 ln of b plus ln of a. Remember that you're taking this 2 over 1 and multiplying it, the numerator and denominator, by 2 ln of b, 2 ln of b. So that's why we get the 4 ln of b on top. So we have ln of b to the 4th plus ln of a, and over here we use the exponent property over ln of b squared, which means finally that we get ln of ab to the 4th over ln of b squared, and that's it. In exercise number 2, we have something that mixes functions with calculus. We have a line with equation y equals 2x plus k, which is tangent to this curve right here, which is a quadratic, a parabola. Determine the value of the constant k and find the coordinates of the point of tangency. Now, in this question, you're not allowed to use your GDC. However, there's a way to plot this quadratic. Of course, without the GDC, we know how to plot quadratics. You can find the vertex, and then the y-coordinate, the x-coordinate of the vertex, and then the y-coordinate of the vertex, and draw this parabola concave up, because we know that a, for example, in this case, is positive. Therefore, it should be concave up. It is concave up. You can start with that sketch. That's going to help you a lot. So if you were, for example, writing this not in standard but in vertex form, you could find the x-coordinate of the vertex with negative b over 2a, and by a, b, and c I mean the coefficients of this quadratic, which in this case means negative 3. And k is found by replacing the h value over here in x. So this is the y-coordinate of the vertex, so we have negative 3 squared plus 6 times negative 3 plus 7, which is negative 2. Therefore, the coordinates of the vertex are negative 3, negative 2. And if this parabola is concave up and the discriminant is greater than 0, then, well, we're going to have 2x-intercept, and it's going to be concave up. The vertex is going to be below the x-axis. Now, how do we know that the discriminant is greater than 0? Well, we can just find it. B squared minus 4ac. We get 8. Therefore, we have 2 real roots. So this is our parabola. Now, do we know the root? Not really, and we don't particularly care about that. We know that there are 2 roots, so this is how the graph is going to look like. Now, we can start answering or addressing the question. This was just a overview of what's happening. And the question mentions a line with equation 2x plus k, which is tangent to the curve at some point. Now, if this is the equation of the tangent, that means that the derivative at that particular point, which is the slope of the tangent, it is equal to 2, which is positive. Therefore, there's going to be some point to the right of the vertex where the slope of the tangent is equal to 2. Now, what does it mean to have a slope of a tangent equal to 2? That means that the derivative of this curve at that point, it is equal to 2. So if we call this a, we know that f prime of a, that is going to be equal to 2. Now, we never found f prime or y prime or dy dx, which is the derivative of this quadratic. We can find it right now. If this is y, then y prime is 2x plus 6. If this was defined as a function f of x, then you would have f prime of x as 2x plus 6. So pretty much the same thing. Now, in what point is the derivative equal to 2? Well, we can take the derivative and force it to be equal to 2, which means that at that particular point, 2x plus 6 will be 2, which means 2x is equal to negative 4, so x is negative 2. So the x-coordinate of that point is negative 2. This is negative 2. And what is the y-coordinate of this point? You can just plug it into here. So negative 2 squared plus 6 times negative 2 plus 7, which is negative 1. Therefore, that point is negative 2 comma negative 1. And that is it. Now, do notice that the fact that we didn't have k didn't change, didn't influence, or didn't stop us from solving this exercise. Do know, however, also that there's more than one way of solving this, and this is the fastest one. Now, you might be asking, what is the second way? Well, if the line and the quadratic, they intersect at just one point, that means that when you do 2x plus k equal to x squared plus 6x plus 7, you should get just one solution, which means that by solving this quadratic, you should get just one root, which means that the discriminant of this quadratic has to be equal to 0. Now, in this case, a equals 1, b equals 4, and c equals 7 minus k. So b squared minus 4ac it should be equal to 0. Therefore, k in this case, it is equal to 3 by solving this equation. And to find the point of tangency, you plug this k equals 3 in this equation again. Or not again, but for the first time, but again using this equation. And then you find just one x value, which is the same a or x value that we found before, which is negative 2. So 2x plus 3 equals x squared plus 6x plus 7, x squared plus 4x plus 4 equals 0. That means that x plus 2 squared is equal to 0. Therefore, x is negative 2. But again, this is a much slower process. Now, on to exercise number 3. This usually offers a lot of trouble for students. Students struggle with this type of exercise. First of all, we need to solve inequalities without our GDCs, so hopefully you remember how to do that. The way to solve inequalities without the calculator is to first find these roots. In this case, I'm talking about, of course, inequalities with quadratics. So you find the two roots, which you can do by either using sum and product or using the quadratic formula, which is much slower, of course. Now, over here, we're going to get x minus 6 and x plus 4 as the factors, which means that the roots, they are 6 and negative 4. And we are going to draw a number line with these roots. So we're going to plug in negative 4 and 6 over here. And we're going to test by selecting one value or one number in each interval to test if in that interval the quadratic is really positive, which is what we want, or if it is negative. So for example, we can test with 0, negative 5, and positive 10. When we throw in negative 5 into our x values, we get negative 11 times negative 1, which is positive. Therefore, over here, we're good. Over here, the quadratic is actually positive. If we test it with 0, we have 0 over here, and over here, we get negative 24, which is not what we want. So we're not going to mark that region. And now testing with 10, we have 10 minus 6, and 10 plus 4, which is a positive number, 4 times 14. So over here, we're fine as well. Now, should we include negative 4 and positive 6? We should not, because this is not a greater than or equal to sign. This is just a greater than. So therefore, the answers are either x is less than negative 4 or it is greater than 6. Now, let's see how this exercise is related to question B. We have a triangle ABC, and given that cosine of theta is greater than 0.2, find the range of possible values of A. Now, we can see a cosine, we can see 3 sides and an angle, so this looks like a cosine rule type of exercise. Let's see how far we can go with it. Applying the cosine rule, and by the way, do know that when you're applying it, this side is opposite to this angle. And you can use either version of this equation or of this formula. We get 49 equals 25 plus a squared minus 2 times 5 times a times cosine of theta. And if you isolate cosine of theta over here, and that's why using this version would actually save you a few steps, we get 25 plus a squared minus 49 over 2 times 5 times a. And we know that cosine of theta is greater than 0.2. Therefore, given that a is positive and 2 times 5, of course, is positive, we can cross multiply, which is something that we need to be careful when we have inequalities. We need to, whenever we cross multiply negative numbers, we need to change the sign. In this case, we don't need to worry about it. So we have 25 plus a squared minus 49. This is greater than 2 times 5 times 0.2, which is 10 times 0.2, times a. So we have a squared minus 2a minus 24, which should be greater than 0. Now, do notice that that's exactly what we did in question A. That's exactly the solution that we got for question A. We know that a is either less than negative 4, which, of course, for a triangle doesn't make sense because a is the size of this side over here, is the side length, or A is greater than 6. Now, if you're thinking, all right, I just got to the solution, there's just one thing that you need to remember, which is this side A cannot be as big as it wants, let's say. It needs to be smaller than the sum of the other two. That's a property of triangles. Any side has to be smaller than the sum of the other two, which means that A should be smaller than 5 plus 7, which means that A should be smaller than 12. Therefore, the final answer is actually this. A is in between 6 and 12. Now let's jump to exercise number 5, which is not that tricky. We just need to do it once just to remember, which is a cumulative frequency graph. Sometimes it shows up, although it's not quite common. And the table that we're going to build in the beginning of this exercise is going to help us build the cumulative frequency graph. The following table gives the examination grade for all students on an IB math course. Well, we can see that they're not doing super well. Only 2 students scored a 7. But let's not judge. Now, given that the mean grade is 4.125, show that P is equal to 17. Now, do notice that P was given. This is a show that exercise, because if it was not, and the student got it wrong, question A wrong, I mean the student that's actually taking this exam, answering this question, everything that follows it would be wrong, right? So this is one way for the IB to make sure that students are still on track whenever they're answering questions B, C, D, and so on and so forth, okay? But I digress. Now, how do we find the mean? Well, let's first talk about what this table means. What this means is there are 3 students who got a grade of 1. There are 8 students that got a 2, and so on and so forth. So one easy way to find the mean, which, by the way, the formula is in the formula booklet, it is to multiply each grade, which by the way is represented by X here. So multiply each grade by the frequency, which is the number of students, which is represented by F over here in this formula. And then divide by the total number of students, which is 63 plus P. Now we have 1 times 3 plus 2 times 8 plus 3 times 17. Then for P, 5 times 20, 6 times 13, plus 7 times 2 over 63 plus P. And that should be equal to 4.125. Now you can either solve it or use the numeric solver to solve this equation. And when you do so, and by the way, pay attention over here, you have P, which is the variable both in the numerator and denominator. You should get P equal to 17, which of course we already knew. Now that we have P, we can complete the column for the cumulative frequency, which is the current frequency plus the one that comes before that. Therefore, the first one is just going to be 3. The second one is 8 plus what comes before, so 11, and so on and so forth. You can view this as, for example, when you're filling in for 5, who got a grade of 5 or less, which means everybody here, or 20 plus the sum of the frequency that comes before. That's the same thing. So we have 65, 78, and 80 as the final one. Now that we have the cumulative frequency table, we can graph the cumulative frequency graph using the grade as the x-axis and the cumulative frequency as the y-axis. Do know that the cumulative frequency will always be the vertical axis. However, the horizontal one will change with the context of the question. So in this case, we're describing grades. It could be, for example, weights or time or anything. If grade is the horizontal axis, which is similar to the x-axis, and cumulative frequency is the vertical one, which is similar to the y-axis, you can view these as points. So for example, you have the points 1, 3, 2, 11, and so on and so forth. And when you plot these points, you should see a curve that looks like the letter S. And there you go. Now onto a simple probability question. A student is selected at random. Given that he got a passing grade, which is a grade that's equal to 3 or greater, find the probability that he scored 6 or more. Well, it's not simple, but it's not super sophisticated. This is a conditional probability, and just as reference, this is the formula for conditional probability. This is the symbol for given that. So we can translate this into what is the probability that he scored 6 or more, given that he scored a grade which is greater than or equal to 3. Now, this is the probability of scoring 6 or more and greater than or equal to 3, which, by the way, is redundant because if he scored 6 or more, then he actually also scored a grade which is greater than or equal to 3. So this is just the probability of scoring a grade which is greater than or equal to 6 over the probability of scoring a grade which is greater than or equal to 3. Now, you can use either the probabilities or the number of students here. I'm going to use the probabilities because it makes a little bit more sense. How many students scored a grade of 6 or more? That is 15 out of 80. And how many students got a passing grade? That is 69 over 80. Therefore, the final answer is 15 over 69, which is approximately 0.217. And that's it. Let's jump to the last exercise now. Now, in exercise number 5, we have, as usual, a calculus exercise. In this case, we have the graph, not of the derivative like we did a few days ago, but this is actually the graph of the function. The function is x squared times ln of negative x squared plus 3, and it is defined between negative 1.5 and 1.5, not including these edges. Now, question A can already be tricky for students. And what this means is the following. Where is the function f of x equal to some number? If you face this as the left-hand side and the right-hand side, what we have is, on the left-hand side, we have f of x, meaning the blue curve. And on the right-hand side, we have the line y equals k, which is a horizontal line. So we're not attributing any specific value for k. We're actually analyzing for which values of k. This equation will have exactly 2 solutions, which means that when we place y equals k over here or somewhere else, we'll find exactly 2 intersections. Now, we can see that over here, for example, it works. We do have 2 intersections up to a given point or up to a given value. If k is anything less than 0, we're going to have 2 intersections. So k being less than 0 should be included in the solution for this question A, but also not 0 and not anything in between 0 and the maximum point, but the maximum point, which if you use your GDC, you find 1.07 comma 0.707. This y value specifically, it will work. So we have these possibilities. Either k is less than 0 or k is exactly 0.707, rounded of course to 3 significant figures. Now that we got that out of the way, let's tackle question B, which is to differentiate f of x. And by the way, let me just say that this maximum point is also 0.707. It is the same value, but the x value is negative. Now, this is an even function, a function where the right part is mirrored across the y-axis. So the maximum here is exactly the same as the maximum over here. Now, onto the derivative. We have the product rule and the chain rule, which will be applied on this differentiation process. We have, let's call, for example, this x squared u. So du dx, or u prime, is 2x. And if v is negative x squared plus 3, v prime is, using the chain rule, 1 over whatever shows up inside the ln times the derivative of what's inside, so negative 2x in this case. We can simplify this a bit and write our v prime as 2x over x squared minus 3. Now, using the product rule, we have u prime times v plus u times v prime. And we can see that in the answer, we have this 2x factored out, and that's exactly what we're going to do right now, factor out a 2x. And factoring out works as if we are removing this term from here and from here. So we have ln of negative x squared plus 3 plus x squared over x squared minus 3. And that's it. That's what we have in the description of the exercise. So let's now jump to question C. Find the x-coordinates of the points of inflection of f of x. Points of inflection are found when f prime prime is equal to 0. So you can, for example, take f prime and differentiate it again. That's not a good idea because it takes a lot of time. And given that this is a GDC exercise, a paper 2 question, you should definitely take advantage of the fact that you can use the calculator. Another idea is to plot the derivative, which you just found, and you have the result for it over here, and find maxes and mins of the derivative. That's going to give you inflection points as well. It's when the derivative of the derivative, meaning the second derivative, is equal to 0. That's why finding maxes and mins of the first derivative gives you inflection points. So there we go. These are our function and our derivative. The function being this curve and the derivative being this one. Now we can find the maxes and mins at x equals positive and negative 0.669. And lastly, to address question D, the function is decreasing the most rapidly when we're at an inflection point where the derivative is negative, meaning when x is equal to negative 0.669. And that's it. We're done with this exercise. All right, so that's it for week number 6. If you've missed any, you can find all of them in the description of this video. Do share away, share this YouTube video, share the PDFs with your colleagues, and I'll see you on the next one. See you next week.